Okay, hey and welcome to example 3. In this example we can take a look at a couple of things. We're going to take a look at the temperature field. We can take a look at the bounding box and the gas resize microsolver. We're going to take a look at a couple of parameters in the Pyro solver and yeah, kind of what temperature does to our simulation. So first of all, we're going to take a look at how to actually create a temperature field in our sourcing density. So we can do this easily with our fluid source. Right now we have a fluid source here that is only creating a density field. But if we want to go ahead and add a temperature field, we can simply click the plus button here and name this one temperature, like that. And we can now see that we have two fields, one called density on field 0 and one called temperature on field 1. They're the same resolutions, and yeah, that's basically it. This temperature will basically affect our simulation just as a hot air rising and cool air falling or staying the same. And this is called buoyancy, the force that acts on fluids in different temperatures. So let's dive into the Pyro solver or the .NET and see what's going on in there. So we're again going to source our density or volumes with the source volume node. In the volume path we put the density 2, out density 2, and this is automatically going to source both our density and our temperature. As we remember, we have a scale temperature slider here as well, so that's cool. And how it's actually doing that is if you go to the SOP to DOP bindings tab, it can actually detect them from here. So if a temperature volume is called temperature, it will add that temperature field to the field called temperature in DOPS. You could potentially call it hello, as long as it's called hello here. And that hello field will now be transformed into a temperature field here. But it's always good to keep it consistent and always call it like what it actually is. So we're gonna call it temperature for now. The same works for density and same works for val. So we can call this like really anything we want as long as we remember to rename them here to the name we have them outside in SOP. But I'm going to keep them density, temperature and val in this course because that's the most easily rememberable and it's a very clean way of working. So we have now sourced the density and temperature with this node here. We're not really going to do anything else here. A new node we're going to introduce in this example is the gas resize fluid dynamic. This one will basically make our bounding box here dynamic. So it can actually adapt to kind of where our actual simulation is happening. So it can kind of detect where it has densities and where densities are not present, which makes our simulations go faster. Because actually this bounding box will determine a lot about how fast and how much resolution we can put into our simulations. Since everything in here is live, everything in here has a density. Even though we might not see it, it's still calculating every single voxel that is in here. So if we can keep this bounding box smaller, that's gonna be way faster and way more efficient. So the gas resize field work kind of as a threshold. So we can define here the subtract threshold and the padding. So if it detects a value that is lower than 0.2 in that sense, it will actually cut it off. We can also add padding, which means that we will actually pad 0.3 on top of that. But yeah, and we also want to switch off this to actually make sure that it's actually fully dynamic, because this will clamp it to our initial volume, which is not what we want at all. We can make it travel with our source, which is kind of interesting, but in this example, we're not going to do that. So yeah, just have a look at this node, get familiar with it, because we're going to use it a lot in future tutorials. But yeah, cool. The smoke a bit stays the same. We're not going to do anything drastic with that. But yeah, that's it for the nodes. Now back to temperature. So the temperature is actually sourced, as we said, with this node here. And the temperature will essentially make our fluid rise where it's really hot and fall or stay the same where it's cooling. And as you can imagine in that case, hot air will rise, but quickly cool off once it's flying upwards, right? That's what happens with any air, unless any additional temperature is added along its path. But yeah, so as I said, buoyancy lift is the actual value for this. So if this is like a multiplier, so if I put 1 in the buoyancy lift and press play, we're not going to see too much. We can see it rising a little tiny bit. We can see stuff happening here on the edges, but nothing major. If you instead put 100 here, boom, it rises quite drastically like that. As you can see, it slows down though, since the temperature is only down here. So all the newly sourced volume or density will travel upwards, but will quite quickly cool off, since no additional temperature is added up here. We can also define that by temperature diffusion. Temperature diffusion is kind of how quickly the temperature spreads in our volume. And our cooling rate is how fast the temperature cools to a lower value. So a cooling value of 0.75 means that for every second we will reduce the temperature by 75%. We can also read it if you hold your mouse over the parameter here. But yeah. And then we also, on this simulation tab, we have timescale, which is kind of a cool node, which actually is a fairly good option if you want to slow down your volume, if you want to make something go slow motion. This is not 100% awesome for that, but it can work in certain situations. And it's definitely cool to put it at 0.5, because that will work great. But 0.0001 is not going to work so well. But yeah. So yeah, and then we also have the buoyancy direction, which is actually the vector of where our temperature will travel with temperature. So if we put this as it is now at 1, our fluid will simply travel upwards. If we instead would put this at a 0 in y, but a positive x value, it will travel like that in x, which is not that accurate, but if you want to cheat something sometime, it can be a cool little thing to do. So that's sort of how the temperature works. I guess we can take a look at how cooling rate affects as well. So now we have quite a high cooling rate. If I put this to 1, which means for every second we're going to reduce it by 10% instead of 75, it's going to look like this. It's going to just keep on traveling. At certain point it will cool off, but it takes a lot longer time, right? So if you put this back to 75 and you put this up to 10, you can also see that the temperature diffusion is much slower. If you put this to 0.05, it's faster. So that can be kind of cool to play around with. But yeah, let's see my notes here. No, that should be all for this. So a little bit about temperature, a little bit about gas, fluid, resize, dynamic field, and a little bit about how to source the temperature. So I hope you guys enjoyed this example. I'll see you guys in the next one. Thank you.